All right, we are live. The first episode of How Things Work. So, thank you to our guests, Alex and Guillermo, for joining us today.
Thank you for having
Before we
us.
get started, I gotta do a quick disclaimer that this podcast is for informational purposes only. Nothing said on this podcast should be interpreted as an offer to buy or sell securities, financial advice, legal advice, or as an opinion of the employers at which our guests work. And then we may hold positions in the companies or projects discussed. So with that, really excited to have you guys on to discuss ZODA, zero overhead data availability, and then the related work, the accidental computer. So with that, we'd love to have you guys give a quick introduction of what you're up to.
Alex?
So you have some of the research and investing team at Bain Capital Crypto here. Guillermo is our chief scientist. He previously tried to name himself chief mad scientist, but
but Alex vetoed it.
No, I specifically vetoed it. Others on the team were fine with it, but I vetoed it. And
I didn't see your suit in the background there. Is that what you're wearing?
Actually, I can tear this out, and it's like a tuxedo. My role is Guillermo sometimes allows me on the research team. Others on the investment team sometimes allow me there. They let me chill out in the respective teams for about a week or two at a time before I ask too many dumb questions or make too many bad investments, and they kick me back to the other one.
He says this
between these teams, I'm at any given time employed. But at all times reading chaos.
You say this, but you're the first author on both of these papers.
Yes,
here, so you can.
He says this, yet I literally try to spend my time nerd sniping this man so we can actually write papers together. And I'm like, stop investing. I know that's what we're supposed to do and stuff, but you need to write more papers.
Well, actually, part of
my diagnosis.
Yeah, we had a busy year last year, and there was a lot of investing and portfolio work. And Guillermo actually mandated.
Yes.
The return to research, which
literally doctor's orders.
And well, I'm glad to be here for episode 0. I think it's a wise choice to have us here, given that we can set the bar appropriately so that every episode is here.
So fair.
Yeah, I'll be dialing the audio in and out in the background, so it's easy to top from here on out. Everything we talk about
real low. Anybody can step over it, and then we're good.
I'm saving my good questions for at least podcast 2. So yeah, this is
so whoever gets podcast 1,
it's kind of a gap podcast.
It's a good warm up. Warm up for people to come out, discuss.
Yeah, this is the pilot, so yeah, we'll see. we'll see what happens.
Yeah, we'll see if we get distracted,
Yeah, but so the quick context here, this podcast, first episode, how things work. A lot of podcasts in the space are geared towards a non-technical audience and really doing the important work of focusing on the impact of a lot of the protocol and research work here to conceptualize it in this maze of ideas we're all going through right now. But usually you steer away from more of the nuanced technical conversation around how they actually work behind the scenes, which is super useful for technical people trying to come into the space to start to contribute, but also to get a deeper appreciation for some of the the insight that's here and how it actually solves fundamental problems that we're working on in the space. And so I think this is a great transition into, you guys published these two papers here. What was the motivation, or what were you guys working on that led to this research?
I think Alex tells this story better than I do. So actually, I'm gonna let you do it now.
Okay.
Sorry, you're speaking twice in a row, and that's
sure,
the way it's gonna go. But
so where did this start? So the germ of this started out. We work, and in the interest, you made the disclosure already, but we work with the Celestia team, we work with the Resiro team, and we actually introduced the two teams at some point, in 2022 or 2023. And because Celestia was looking at how do we prove inclusion of various things inside of the data availability layer, and then also do we want to prove correctness of the encoding, how performant is this prover actually? And I mean, both projects were a little bit earlier in their development, but somebody from Celestia, I think it was Jacob R, messaged me being wow, I didn't realize that a lot of the techniques these folks in Starkland and Resiro are using and the stuff we're doing is actually similar. We're both using Reed Solomon and hashing some stuff. And I was yeah, that is kind of interesting because if you look at the people that work on the data availability stuff, they're not like people. The others are not sort of necessarily always blockchain people, though obviously there's been more overlap over the years. So people were using very similar techniques. I just filed it under like mildly interesting, but it was kind of in there. And then we earlier this year announced the addition of several people to our team, particularly researchers on the advanced cryptography side. So things like ZK and PC, sort of interesting new theoretical constructions in advanced cryptography. And we were talking to that group, which at the time, a bunch of those folks were at this firm called Geometry Research. And we were having a conversation about, okay, should we work together? Like, we already were collaborating on stuff.
Sure.
We'd hang out, we would work together. We'd co-invested actually in the past because they used to be part of an investment firm. We liked each other and the vibes were good. So we're just having a conversation of what is everybody working on. And Nico, who's co-author on the ZODA paper, mentioned his work on Fry and particularly data availability from Fry. And so he mentioned essentially this sort of protocol that he was looking at to sort of create a slightly more efficient version of that. And as he was describing it, like this sort of idea that was like filed somewhere in some dusty cabinet in our mind just sort of resurfaced, which was like, oh, wow, like what you're actually doing here is, you're taking an encoding, you're hashing it, and then you're querying it. And a lot of ways we looked at the protocol a little bit more deeply, and this was at the point at which Guillermo mandated, like sort of as a form of or torture or punishment, I don't know what, to sort of go back and do research. So it's like when it was in July, sort of Guillermo sat me down and was like, look,
I was like, dude, like you need to come do research. Like
we're losing you. Yeah.
Patient will not survive. Yeah, and so anyway, so I just looked at it, and like one of the things that came up was there was a lot of overhead to the construction. We should get to defining overhead a little bit later, but essentially what the construction is that you pass around this like big proof on the network that the thing was correctly encoded, that everybody would download be the same proof. And it was this non-interactive proof as we're used to in snark land. Somebody goes in their head, uses like these generates a big thing, and like, everybody downloads it, checks some things, everything's good. But like that seems expensive. And also typically what we start with is an interactive protocol. And then we compile it down to a non-interactive protocol. But like, hey guys, like we're already in this DA setting. And we should talk about the DA setting, but long story short, we're already in the setting where people are non-interactively downloading random things. I should go back and unpack
interactively downloading random things.
Right, interactively. You corrected me on another conversation the other day on this exact. So that was the original insight, was can we leverage the work that people are doing anyway to come up with something more efficient? And
so that one
cleared the bar of a good enough nerd snipe for people to like want to work with me on it.
Right.
It is an interesting insight that like a lot of these protocols and systems are already so complicated and complex that the idea that you could somehow like reuse work from one and another like kind of breaks, I think, some of the best practices around like trying to do stuff. And so like the idea that you have the purview kind of across two unrelated or like seemingly unrelated problems to see the similarity is an interesting insight.
So that insight actually was, although we used it in ZODA, came out originally in a blog post a few weeks before, a month before. I don't recall what it was like.
Sampling for proximity and availability.
There we go. Sampling for
proximity, which is what Fry is, and people sample for availability. What if you just sampled once for both?
Yes.
Does that work, or does something fundamental break? And that was
idea. And so you'll see this. I mean, this is kind of a subthread of a lot of our work, which is we take a thing that people consider usually fairly complicated, right? And so what happens is like, what happens in a lot of these constructions, for example, is people black box the like so-called like snark part. They're like, cool, I now have a proof that this thing is good. What can I do with that? Right. But the observation shouldn't be like, I have this black box. I like now prove an additional thing on top of it, which is I have this proof and then I sample some extra things and I know that those things must be good. Right. The observation should be like, wait a minute, like the black box is itself like made up of parts that can be like individually understood. Right. Which itself actually is already doing the thing you're going to do anyways. So, and you'll see this a lot in the, not just this work, but even prior work, where we spend a lot of time as like, taking the big machine, like taking out all of the screws, like taking out all of the gears, polishing them a little bit, like, and then putting it all back together into a smaller machine that just like works the same way. It's perfectly fine, but like doesn't reuse these like, black box components. It's like, okay, no, just like make the machine that you wanted to make in the first place, rather than start with like a thing that you already know is good and then build on top of that, right?
Yep.
Which is, in my opinion, like it's kind of like in some ways the, really, really fancy engineering work does this, but most engineering work is much more predicated on like, let's take these black boxes, put them together, which is already very good and it's very cool. But
I feel like it's almost like just a maturation of like some of this technology. Like I feel like taking the time to like kind of take things apart and see where you can share stuff is really not a useful activity if it changes everything in 3 months anyways.
That's right.
But like I think as we like continue to move further right on the curve of like maturation of like all of these protocols, it actually is like, hey, like there's actually some shared stuff we're always going to build on here, and like we have no fucking idea how we would not do that.
Yep.
So yeah, maybe I think it makes sense to actually go into like some of this, how the actual DA constructions typically work, and then particularly like maybe what that overhead is today.
Yeah.
Because I think a lot of people talk about, oh, like DA, and I think most people, and this is a shame, but like think about it as like, oh, I'm pretty much just uploading data to like an S3 bucket, and then like other people can call it, or like, and so the idea that there's actually a lot going on here to both like understand how to break things up and then to show somehow that like what was broken up is correct is a very interesting space to explore. So maybe we start there and kind of go into a little bit of how that works.
So before we do that, I want to echo something that you said, Patrick, that I think is really interesting in this work, but also a lot of our favorite work, which is sometimes you'll see in doing this exercise of polishing out the components and breaking them out.
Yes.
Like two different sort of seemingly unrelated fields. You notice actually this component is the same. We are talking about the same thing. And this is an example of that. It does come from cleaning things up by sometimes you'll see sort of a sequence of works. And the first work will be people are doing a thing, let's clean it up. Guillermo had this with automated market makers. We had it with fees. And then this would be a second, so fees for blockchains. And there'd be a second work that then is like, okay, now that we've taken this stuff apart, let's go reassemble it into something interesting.
That's right.
And a lot of stuff. What's there's this consensus mechanism that you all are really interested in as well. There's a predecessor, is just like the Streamlit stuff, which is like
Simplex.
Yeah. It's like you just see the same pattern in a lot of different places, which is like here's like a really simple way of describing a consensus protocol that I can explain to a high schooler.
Yep.
Right. And high schoolers are super smart. Maybe middle schooler. Right.
I wish I was that smart in high school to understand that.
But now it's like, oh, actually, like with that simple construction, we can come up with something that's like close to the frontier of state of the art, if not better. That's also equally simple. And so as fields mature, which is exactly what you said, and I totally agree with, like this ends up happening. People just come in, they clean up some stuff, and then they can sort of very quickly like take what they need and don't need. And
I always think of that quote.
That's magic. It happens sort of automatically because we'll end up working with like a risk zero and a Celeste. So we're like kind of be in this amphibian state often just by virtue of the fact that the investment work is so wide that it just leads to interesting research insights. Anyway, not to get too much on the meta point, but I really like what you said there, Patrick.
Yeah, I think I always think back to that quote of like, what if I had more time, I would have made it simpler or something like that, or shorter. And I think a lot of times, like this is why things tend to look like overnight successes. Is you like have all this work that's going on in the background, and then ultimately end result is like some simple thing that you should have seen from the beginning. And so you're like, oh yeah, of course. Like, and you don't see like all the time and polish that went into getting to that simple point. But yeah, so let's get into what that complex part was, and then like kind of break into maybe like what that clarity of thought ended up being with ZODA, and then we can kind of go from there.
Yeah. So I guess there's like two pathways to it. Number one is like Alex mentioned, there's earlier work, which the TLDR of it is like all of these things are essentially linear algebra, right? And that is while it sounds kind of silly, especially now, although I think at the time people did not actually believe that Fry is like fundamentally linear algebra or whatever, and we still get badgered about it every once in a while. Like that is a hugely clarifying perspective. Actually, I think that's, funnily enough, I believe I was your TA for linear algebra, right?
When we first met back at the university. You had gotten deeper into linear algebra and seemingly saw the future coming, and I was more so just trying to check that requirement off the list. So I'm glad you proceeded on and
continued,
I'm glad you're having fun. Yeah.
That's good.
Yeah.
Background, so
Yeah.
I
I'm kind of screwed here. I ended up on a call with 2 Stanford linear algebraists quizzing me on things. It's not looking good, Chief.
I wouldn't say I'm a linear algebraist, so don't worry. Yeah, go ahead.
So there's one path, which is like, look, a lot of these succinct proof systems and techniques that are used to succinct proofs are all kind of very basic linear algebraic structures. There's a little bit of detail in it, but not too much. And there's a second point here that's going on, which is Celestia, kind of by construction. So this linear algebra, essentially, like TLDR, what it looks like is you encode a bunch of things, and then you perform operations on those encodings. That's like 99% of what you do in many succinct proof systems is essentially that. Mm-hmm. And there's that, and there's like Celestia, right? Which is cool. We take a piece of data and like we encode it such that if you sample enough pieces of that piece of data, you can recover the original thing, mm-hmm. right? But in some sense, that's actually the same reason why the underlying proof systems work. It is this idea that if you do 2 things. If there's a mistake, it is encoded in enough places you can always catch it. And then number 2, it's if you sample enough things, you can actually recover the original piece of like underlying data, right? Like the thing that like the prover must have had in their head to give you the proof that passed, or enough proofs that passed.
Mm-hmm.
So
just to be clear, right? Like when a block is produced in something like Celestia, the builder like creates some block, and then they basically cut this block up into a bunch of pieces, and then they do something on top of that to send with that
exactly
slicing up
to
show that it's correct.
I can very quickly describe what Celestia does today.
Sure.
So they take a bunch of data, and data you can think about it as like a big vector of a bunch of numbers, right? And these numbers are going to be numbers of a finite field, but it doesn't really matter. It's a big vector of like a bunch of U16s, like UN 16s. And then that vector is going to get rearranged into a matrix, right? So you have a n squared size vector. You can rearrange into an n by n matrix. And then what you're going to do is you're going to encode both the columns of that matrix, right? So every column is going to start with n things, and you're going to create a new vector, which is of size m, right? And m will be larger than n, usually 2 times larger, such that if you have from this new big vector, if you have at least half of the entries, you can any half of the entries, not just the original n, but any half of the entries, you can recover the original n entries. So this is an error correcting code because of the fact that you could imagine some of these entries are missing, right? If you only get half of the entries are missing, and we can correct those erasures or errors if they're some of them are flipped or screwed up. Otherwise, you can unscrew up those errors and recover the original piece of data. So Celestia does that. So when we have a matrix, we now take every.
And then just to briefly interrupt you there, the m value, basically the size of that determines how many pieces can be lost before it can be recovered.
Exactly.
Is that? Yeah,
Exactly. So if m is, like whatever. So m, just assume for now, m is twice the size of n, right? So that means that you have twice the redundancy as you have. This is not always true for all codes, but for now it's good enough. Such that like that's twice the redundancy, which means that receiving 50% of entries is good enough. You can imagine m could be 4 times the size, in which case you only need 25% of the entries to recover the original vector. Okay, so that's the columns. And then what you're going to do is, you now have a big, you have a tall and skinny matrix, right? So you had a square matrix, and now it became a tall and skinny matrix. And then you're going to encode the rows of that new tall and skinny matrix using the same idea, same trick. So you're going to take each row, and then you're going to blow it up to twice the size, such that if you have half of the entries of a given row or more, then you can recover the original data of the given row. But any half of the entries suffice. So now you have started with a square matrix, you blew it up to a tall and skinny matrix, and then you're going to take it and then blow it up into another square matrix. Cool. So that's what Celestia does today.
Got it. And then just to be clear, as we're like talking about this visually, right? It's like tall and then it gets wider. There's kind of like a gap in the bottom left-hand corner of your diagram, right? So
I'm also including the bottom right. So you're also putting both the rows of the original data, which would be this top stuff, but also the rows of the bottom thing, which are these already redundant pieces of data. You're encoding those as well.
Interesting.
Right.
Cool. Okay.
So for the technical people, it's called a tensor code. It's, it might come in handy later, but okay.
That was one of my buzzwords I wrote down. I was like, I'm definitely going to try and get Guillermo. Let's talk about it.
If you're on audio, imagine you take a square, you encode it. In other words, you double it just on one side, and then you take that whole thing and then double it on the other side. So you end up with something 4 times as large. So
got it. So it's like down and then the whole thing left rather than got it.
Exactly.
Even though I said I would do it verbally, I still, I don't know if there will be video or if this is just audio.
There'll be video. So yeah, your hand gestures will come in handy.
Being as I am Greek, I rely on them heavily, and so that is very encouraging to hear.
That makes 2 of us. Not the Greek part, but the relying on hands heavily. So that's what Celestia does today, right? And the idea is the following: if you have enough people taking enough entries of this like big matrix, if the encoding is good, and that's a big if, but if the encoding is good, then let's say that like the person who is serving these entries like goes away, right? Then these like people can get together, and so long as if they collectively have more than, in this case, 75% of the data, they can recover the original piece. So they can recover the original piece of data if they have any 75% of this big square. Okay. So what's the idea behind Celestia? There's many ways of seeing it. My favorite, which is like a weird translation of it, is Celestia gives you, so you post some data onto Celestia, and Celestia gives you a certificate. And that certificate says you have indeed released the piece of data that you said you released publicly. So that is, and the way you guarantee that is it gets included into some block and enough people sample it such that like this thing has to like pass.
Yep.
Right. And if enough people sample it, you know that either, even if you somehow withheld the additional information after the fact, if all of these people accepted, in other words, they sampled and got the shares, then they themselves can go and reconstruct the data the original data.
Yep.
Yeah, this is where people get sometimes a bit confused, which is what you were asking about, Patrick, too, which is this isn't sort of it's not telling you about where the data is stored.
This was exactly where I was going to ask. Yes. Yeah, like how is this different from something like a Arweave or like a long-term storage mechanism?
Yes,
right. Yeah. Right. So you think about these things as 2 separate concerns, right? So if you want to persist something for a long period of time, that's a you problem, right? That's maybe there's good protocols for long-term storage of things. Yeah, but I would think about this more in the vein, people like to call it sometimes proof of publication, like efficient replication or whatever else. It's just that you actually sent the thing to some set of people. And between those people, even if you're not cooperative, they can like recover it. But how long, for instance, those people that you sent it to hold it is a protocol parameter. It's actually sort of a separate concern.
Yes.
And so yeah, people do think about it as like a sort of an S3, or that like I'm quote unquote storing data in a data availability system. And I think it's appropriate to think of those things as large.
Yeah, exactly. Just, the way I think about it again is like when you post to Celestia, the point of Celestia is to give you a certificate that everybody else can agree means that you posted that data publicly, right? Because of the way the protocol is constructed, right? It says nothing about storage. It's nothing about how long a piece of data is available, just that you put it publicly in some billboard and like everybody agrees like that was cool. And you indeed posted this data publicly.
Yeah. In practice, some of these protocols will have different expiry mechanisms for like just clearing out old stuff. The idea is you just want to get it in a lot of people's hands, and some people want to store it or iCloud or like on Arweave.
If you're storing your blockchain backups on iCloud, you maybe want to look at that.
It depends on the blockchain, Patrick. Where we're going.
Hey, I'm just exploring how things work here. I have opinions of any kind.
Yeah, you're just asking the questions, you know.
To be clear for the audience, that is not how things work. That was a joke.
Well, I don't know. Some blockchains, you never know. But anyways, okay. So Okay.
So we got this square. All right. So like, how do I know that like if I'm a sampler, let's say in this case, that like the square I got, if I pick, you know, a bunch of random ones, first of all, which squares do I pick? And then second, like how do I know that the squares I got are actually validly created? Yeah.
So the network, so we're gonna like now get into the like slight religious beliefs, but I'll explain what that means in a second. But the network is essentially made up of light nodes, which are going to go sampling light nodes. And sampling light nodes for now, I'm just going to describe their behavior, and then I will tell you something what it means in just some aggregate settings. Sampling light nodes are going to just take some random entries of a square. So you have a big square. There's a bunch of entries in it. Just randomly sample a few of them, however many you want.
So it's their local randomness. So it's not like some synchronized randomness.
It's
so
their
they,
local
on their,
randomness,
got it.
They toss a coin in their own head, and they use that coin to figure out what entries they're going to sample. And the point is, like intuitively, is if some parts of the block are not available, right, then with high probability they will like sample. If too much of the block is unavailable, like they will sample something that's unavailable, and then they will not accept that block as being good. But okay, this is maybe getting ahead of ourselves. So that's what the samplers do. Okay. Now you might ask, okay, what guarantee does that give? And the answer is like, in some sense, it depends on your religious beliefs about who else is also sampling. It only gives you a guarantee that you can reconstruct the data if the block is unavailable, if enough other people are also sampling, such that if you get together with them, right, you can reconstruct the block in spite of it being served or not.
Because the whole point is that you, as like these clients that are like these light client sampling nodes, as you mentioned, you're like, if we could just download the whole block, we wouldn't need any of this. The
Correct.
whole point is that you're trying to not have to download the whole block, to have some understanding of existence.
That's exactly it. Okay, so the important thing, and this is hopefully going to segue us to ZODA, is there's a very important assumption that we like have swept under the rug this entire time, which is we can only collectively recover the block with enough shares, right, enough samples, if the block is correctly encoded, right, which is a big if, right? Like if you can imagine some adversary is not doing, you know, encoding random stuff that's actually completely irrelevant and claiming that they're good encodings. So the way Celestia gets around this right now, and I'll let Al explain KCG in a second, but is you have a further assumption, which says we're going to have one person potentially running a big computer download the whole block, and then if there is any part of the block that is incorrectly encoded, it turns out you can construct a short proof that a part of a block has not been correctly encoded and send it out to everybody. So the assumption is that there exists at least so every sampler is sampling, and they're just going to optimistically assume that all their samples are good. So such that if they are connected to at least one honest node that is downloading and verifying the whole block, then, you know, if there is indeed some error in the block, they will be alerted and therefore not accept that block as being good.
So right now, the light clients are basically just sampling for existence. They're not sampling for any sort of correctness of encoding.
Exactly.
Okay, got it.
Exactly. And in general, right now, like the use of these full nodes is fine, right? You know, encoding what is right now, I believe, 8 maybe bits is pretty fast on a single core of a laptop. Is like I don't even think it's like even close to half a second. But okay. So anyway, so that's a big trust assumption. Now, some people have tried getting rid of this, and so Alex, if you'd like to explain this to us.
Yeah, so the one thing is, of course, the trust, which seems fine, right? It's like I am connected to somebody that can encode, 8 bits or whatever and can download them. That probably seems okay. But of course, a lot of people now are doing redundant re-encoding. And so every full node needs to do it. Everybody that's participating in consensus that currently actually needs to do the whole thing. They're not even doing it over subsets of the data. That you could imagine sharding it in some reasonable ways. But that produces a little bit of overhead and creates a bit of an additional trust assumption. So what people have tried to do instead is, can we create proofs of correct encoding more in the traditional ZK sense? So obviously a very trivial way of doing this is like what we actually looked at doing in the original conversation between Celestia and Reciro is, can you just take this encoding process, which is I'm taking some data, I'm encoding it, I'm hashing it, and then give you a proof that it was correctly encoded, right? Because I stuck it in a general purpose thing like RISC-0 that generated a proof, and give you that proof, and then you can sample components of it and know that you're good. There's slightly more intelligent versions of this that are much more practical. One that's considered in Ethereum, I think a couple other protocols as well, which is using what are called KZG commitments. We don't need to get super deep into that, though there's some limitations to that. One, sort of not post-quantum secure. They sometimes rely on trusted setup for huge data, actually, like the size of that trusted setup actually ends up being too big. And then there's other ones in that there's quite a bit of prover overhead. So if you want to compute commitments and then a ton of openings, there's a bit of a trade-off. You want your openings to be really small so that nodes can be really small. Then that imposes a lot of prover overhead. So in practice, people try to interpolate these things to make them practical. But these are considered very practical protocols, to be clear. They have very low overhead.
Because I mean, KZG is used in ETH right now for like blob data encoding, right? So like there is like a massive practical usage of it today.
That's right. That's right.
Yeah.
That's right. And is contemplated as part of this, like, for really big stuff and with like sampling of individual, it's, considered to be very practical. That said, it does still have a fair bit of prover overhead. It does have a little bit of sort of proof size, or that you need to download these opening proofs and so forth. So while now you remove this redundancy, you also need somebody to do sort of these encoding. I think some people have even talked about using GPUs for that. And so now there's complexity involved there and like a sort of slightly different trust assumptions, the weaker ones. So anyway, there's some benefits to it over the fraud proof-based construction, but then there's other much hairier issues with DA that we can get into, which is that if you withhold some portions of the data, but not all of it, then somebody might need to like go and recompute those proofs. And so it's been debatable whether like that is a better approach versus just doing the fraud proof-based construction right now. And indeed, like some protocols, in this case, Celestia, have chosen to just stick with the current construction.
As they say, it's all trade-offs all the way down. Yeah.
Yeah, always.
They do be that way.
Unfortunately.
Turtles, if you prefer, but yeah, trade-offs is also yeah.
So yeah, where were we? So okay, so our proposal here is at least what we first noticed with this Fry thing turned out to be more generalizable. So we published this original post. We looked at an encoding that you would do inside of Fry. So how does the Fry protocol work? Fry protocol takes some data. Typically, they interpret as the coefficients of some polynomial, and then they evaluate that polynomial on more points than there are coefficients to get some reasonable rate. Of course, that's just an encoding, Reed-Solomon encoding, and then people sample that and do some additional consistency checks. So it turns out that just by doing the former interactively, which is normally in Fry, you would do some queries at the top layer. If I do those queries and you do those queries and Guillermo does those queries, then of course we end up like downloading the same stuff. So it doesn't really tell us anything about the original data. We haven't learned anything that between the three of us helps us reconstruct the original data. For instance, the block proposer goes offline or is like otherwise malicious or the network's unreliable or something like that. So the first observation was like, can we get people to like sort of sample these things interactively? So if I'm going to download a proof, I'll do it with interactive security. You'll do it with interactive security. Guillermo will do this with interactive security. We'll get roughly the same security guarantees. But now we'll also, between the three of us, have learned new information. So that was the first observation. We still ended up with a little bit of overhead because Fry, we didn't have to get super deep into it. It does these additional sort of redundant, what are called folds. And those things turn out to kind of be useless for reconstruction. So everybody needs to download, for the symbols, they do download a whole bunch of like additional sort of, think of it almost like metadata. It's not quite there.
And that's, you need to download that basically to verify what.
Yeah, it's like sort of a kind of proof object.
Yeah, like think about it as like those things only help you insofar as they tell you that the data is correctly encoded, but they don't actually help you to code the data. They just tell you the data is correctly encoded.
Yeah, got it. I mean, I guess that there's like some naive intuition there. It's like, all right, I'm giving you the data itself, and now like here's kind of this little extra stuff so you know that it was right. So like you could see how that was the progression into what that is.
Yeah. So anyway, we started with like originally you would get like a tiny bit of data and a lot of proof, for example. And we're like, okay, that maybe is not like, that's probably worse than the equivalent thing. And KZG certainly has much more overhead than KZG. And still, like right now in the fraud proof construction, there's no proof in a fraud proof based construction. Your proof is a religious belief that like you're connected to like an honest full node. So it wasn't really like a fully satisfying replacement for that thing, though it does have this cool like post-quantum property and is actually quite a bit faster to encode because you can choose whatever field you want and all this stuff, which is awesome. And you do need to generate like all these opening proofs, which is like actually quite a bit of the overhead, and things like KZG is actually computing these opening proofs, which are much slower than even committing to the polynomial. Okay, so promising direction, but like now you have to download this massive proof. Interesting progression is, can we just do that interactively so that we still have to download that proof, but it's actually useful for reconstruction. But we still end up with a little bit of this proof object. So our thought, or at least hypothesis, was, can we actually take that to 0? So given that we have a little bit of prover overhead, people need to compute these intermediate folds, which is prover overhead, and people need to download those components, which is sort of node overhead. Think about network overhead is what we call it.
Yeah. So just, we've had this thing, and it's appeared a bunch of places, which is like succinct proofs in general are like this big object, right? Like you do a computation and you want to prove the computation is correct. This is just like stepping back a hot sec before we go back into it.
Yep.
But like the problem with succinct proofs is that like computing the thing you want is like very cheap often to do in a computer, on a phone or a laptop or whatever. But computing the proof that the thing was done correctly is like really expensive. It's like many thousands of times over.
Yep.
Like, you know, then it takes you far longer to do that than it does to like actually compute the underlying object. So
for the folks with the real-time proving interests, this is that part. It's
exactly.
Like, how do you actually get this fast computation provable and then quickly verifiable? Yeah.
So the thing is, like, the reason why a lot of this overhead comes in is because, you know, proving systems or in general want to do this like general purpose compute. And like, that's cool because look, I can just throw whatever I want in there and like, we're like chilling and like stuff is cool. And like, that's great because it means you can just write code. The problem is like many of the problems that we spend a bunch of time, you know, kind of solving or like computing stuff over or whatever are actually very structured and very specific. And so the natural question is, cool, like, do there exist certain things, certain problems, certain computations where, you know, the computation is actually like almost or close to like this, you know, 90% of the work, and the proof is only like a little bit of extra work or something like that, right? In other words, like, are there special, the way to think about it is, are there special purpose like proof systems that prove like one very specific thing very, very, very quickly, right? Relative to like, you know, the computational time it takes to actually compute the underlying object that you're looking for. And so this is like, just think about this as like a through thread of all of the stuff that like now leads to this question. So anyways, go for it, Alex.
Yeah, so here's the hypothetical, right? The hypothetical is, okay, you could take a general unstructured computation that's a black box that you know nothing about. And we know increasingly through the work of various excellent teams in the ZK space how to do that faster and faster, like closer and closer to the native compute. And also like sort of the real-time proving is throw a lot of hardware, since you can parallelize the proof side of it so that it takes about as much time as you could compute the thing. And that we're still working on, but people are making great progress on. So that's a great tool. However, if you think more carefully that certain computations are highly structured, could you come up with meaningfully more efficient constructions? Right, like Andrea on our team has this great paper from last year around proving pairings, for instance. Okay, this is a highly structured computation that you're using this pairing-based stuff to prove. Like, okay, like you should be able to do better than like just think about it as like an abstract like computation on some Turing machine that like you reduce to this arithmetization of this thing. Like you can be a little bit more creative about it. So what would be the perfect version of this? The perfect version of this would be if I could compute something and give you the result, and you could verify that I computed that result correctly. The ideal is I can compute. I only need to do the work required to compute it and nothing else, or close to nothing else. So I just need to compute it. And then the proof size is 0. In other words, I just give you the result of that computation. And just by looking at the result and additional proof data, or as close to zero proof data, just doing some local checks on your side, you're good.
Yeah. So like, in other words, can you construct an object such that its existence or its like construction is its own proof of its own correctness, right?
Very
or like
cool.
small bits of it is enough to prove its own correctness. Like you just look at a few rows and columns, like, or whatever, a few little bits of the object, and therefore you know that the object must have been good, right?
Magic. So I guess like the question is like that is, I mean, I suppose like the pretty close to the optimally minimal way to do something like this, right? Because like you're basically just giving like some overhead of the data for error correction and then nothing else, right? So like you're basically bounded by communication theory at that point around like how minimal of information you could share.
Yeah. In some sense, like these error correcting codes, because they're used in these proof systems natively anyway, right? Like normally they'll take, like what does risk zero do?
Yeah, sure.
They go to computation, it'll reduce it to a system of polynomial equations. It's gonna, I don't know, I guess like take some kind of quotient to reduce that thing to like a statement about the proximity of a polynomial to a code word, which then you're buried a bunch of points to verify, right? But like, what if the original thing you're trying to prove is the proximity of a code word to a polynomial? Like, why can't you just like skip all these steps and just skip the thing that you want to do? So what we were doing before is that we were taking this Celestia construction or whatever it is, and we're taking that and we're putting it inside of a general purpose proof system. So we're encoding this thing natively, we're hashing, and then we're putting it into a side of a circuit that's going to encode and hash and reduce something to an encoding and a hash, which is just a little bit unhinged if you think about it in hindsight. So in this case,
I mean, it follows like how you kind of develop in the space, though, right? It's like the same sort of thing, right? Like ideally, right? There's like I don't write my own language that's like super particular to what I'm doing, right? Like I write Rust, which compiles into like LLVM, which then compiles to my processor architecture, and I like you can understand why people want to do this, but yeah, you pay for that. That's why back in the day people used to like write these like massive stacks of assembly code, right? Like that was the way people wrote code, and like it was faster. But as soon as we no longer had to do that because the processes were fast enough, we
that's right,
the easy way out. But yeah, it turns out like in a resource constrained environment, there's some juice to squeeze. Yeah.
So I would be careful because we're actually switching back, right? I mean, now we have special purpose chips in our processors that run explicitly linear algebra operations to do like tensor operations, which tell you like your neural net is like doing the right thing or whatever, right?
I think I saw this article from a few weeks ago that Meta like is now building a compression chip, like for their large scale like streaming compression. It's so much faster than anything they can do in software. So I mean, I think of it as this. I almost think it comes back to that original conversation of like it's this pendulum of like you don't know that these things are related, so you end up building all these like very particular systems on a chip or whatever, and then all of a sudden we figure out like some universal way to make everything faster or better that unifies it, and then you're like, oh, actually we just need like a bigger CPU because it already does everything we need, and then you kind of like swing back like, well, there's these edges, and then so I think it's interesting to see how I agree, like the specialization of hardware and some of this stuff is definitely now coming back as it needs to differentiate. And I think, at least for what we work on at Commonware, I think it fits like right into this hypothesis of we think that there's a room to specialize and then as a result differentiate in some meaningful way, and that we're building software to do this. Now, we're not building any software of this variety yet, I suppose. But, we'll see.
But presumably even there, a similar thing will happen too. This is a slight tangent on ZK VMs and like the ZK space and maybe the broader sort of decentralized and crypto ecosystem is you'll build these great abstractions where people can just like not have to think carefully about what they're doing, and it just handles a lot of the rest for you. Through that, you enhance the range of things that people can do with low friction. Then you're like, oh crap, I'm doing this thing again and again and again, and I'm paying a lot for it. So let me think about how to specialize it. So yes, I don't think it's a reasonable thing for every person, every potential customer that you talk to like have to think like from first principles of like, how do I go find a stand to build my own processor to do the thing, right? It's just like, I want to do a thing, like give me the right set of tools to go do it. And then like, oh crap, I'm paying a lot for this. Okay, let's sit down and have a conversation about how to optimize it. But yeah, if we had to do this for like every random thing that we would have to,
Oh man.
like, I mean,
Yeah.
Guillermo would come in here, you'll see this chicken scratch. He'll like write whiteboard. He comes in here like, a couple times a day, and then he'll write some crazy stuff on it. And it takes months to like think about, but it just happens to be an operation that we know is constraining to some of these systems.
I think it's just that like it goes from that like can we do it to okay, can we do it better?
Yeah.
And I think that's hopefully the thing that pushes us forward. So yeah, I mean, I'm curious now. So like we've gone over like the original, kind of insight and like some of the insight into like what takes us to ZODA. So like I guess where is it at today? Like are people now trying to take this and utilize it? Like are there any issues you've noticed like since the publication of it? Where you're like, oh, we hadn't considered that, or there's like some unexpected cost we
so do we want
weren't
to
aware.
Review what ZODA actually is? I don't know, Alex, if you want to go ahead, or I can do it.
Yeah, just go ahead briefly, maybe, and then we should talk about the thing you put out the other day. It was a fun troll. And
that was a great troll.
Talk about, I mean, you sort of jump to the conclusion about it. It's what you said earlier. Like there's trade-offs to everything. So there's trade-offs to ZODA. There's stuff that we identified in the paper as interesting areas for future work, particularly stuff around node size and so forth that we're doing a bit of follow-up work on. When you see these things published, it's never like the first version of it that's like perfect version of it, but it's already quite interesting. So anyway, Guillermo, go ahead.
So really quickly, right? We talked about these encodings, right? Where you like take a square matrix, you like tall and skinny, and then you like make it square again by like re-encoding. Okay. The idea is very, very simple and almost stupid, right? Essentially, like in the process of encoding, there's like this very normal operation that happens in these proof systems, which is you take a bunch of vectors, right? So a matrix you can think of as a collection of vectors, which are its columns, and you randomly combine them, right? And there's a test called the Harrow proximity test or subspace distance check or whatever you want to call it that tells you the following. If you take a bunch of vectors and you randomly combine them and you check that the result is close to some code word, in other words, it's close to some correctly encoded vector using this error correcting code, then, this is very magical, each of the original vectors must themselves have been close to a code word. In other words, like the vectors in the matrix that you randomly combined are themselves like mostly correctly encoded. And that's the trick, okay? So that's the basis of this idea. And the point is, okay, cool, but like what is a random linear combination? Well, first of all, what is a linear combination? Well, it's you take rows and you like multiply them by some vector, right? So that's what happens when we're extending this matrix out. But if you're slightly just like tilt your head and look at it, it's like, wait, if I squirrel away a little bit of randomness in how I encode, then this, encoding, this new encoding that you do over the rows, right? So we've encoded the columns. This new encoding you do over the rows itself becomes a random linear combination of the like original columns, which you can then use to verify that you actually correctly like encoded the original things. So the idea now is like, because you've kind of squirreled away the randomness into the encoding itself, there is no additional data that needs to be sent. Because
can you be a little bit more specific on like what that squirreling away randomness is? Like, I pull out of my pocket or like where?
Yeah. So the randomness, this is a great question. Yeah. So the randomness will come from Fiat-Shamir randomness. So you're going to commit to these, like this matrix, this like now tall and skinny matrix, right? You're going to commit to, I don't know, the rows of that matrix. And then you're going to use that commitment to derive randomness. The cool part about that is that we all agree what the randomness is, right? Like we all agree that like the random values that we're going to use in the proof are the following or whatever, SHA of that, SHA of that, SHA of that. Or whatever.
And practically like that commitment is stored like let's say on a blockchain or something like that prior to the encoding. So that's how you forcibly commit to something. So you
exactly
start to change to get better randomness.
So yeah, the commitment you're going to use for two things. Number one, you're going to use it to create randomness. The commitment is very small, right? So it doesn't really matter. The commitment is 256 bits. So you can send that without even thinking about additional.
Yeah, you're going to send it alongside because it'll be deterministically derived from the commitment. But ultimately, like imagine the setting where you have a proposer that proposes a block that they want to claim availability for, and there's going to be a commitment to the underlying data, as opposed to obviously you can't send the whole block that, for instance, they're going to sign.
Yep.
But then you're going to sample against that commitment later. Mm-hmm. And so when you sample and you're doing your checks, you know what randomness should come out of it.
Yep. Exactly.
And that basically agreement on randomness is super important, obviously, for this encoding process.
Yeah. Right, because the randomness that we use is going to be the randomness used to generate the new columns. In other words, the proofs, which are like squirreled away in this matrix, but also it's going to be the randomness that we use to verify that the columns and the rows are consistent with each other. And the beautiful part here about ZODA is specifically like what you're going to do. The one additional check you're going to do is when you download some rows and you download some columns, you're just going to check that like the intersection of those things is consistent. And that's enough. Like that ZODA claims, the whole claim of ZODA is like just checking the intersection points is enough to guarantee that the original thing must have been good if you do enough sampling. So the point is like, it's weird, right? Like it's very weird. It's like all you're doing is you have a thing and the thing itself is its own proof of its own correctness that you can verify by like taking subsamples of that thing and then checking that they're consistent in the way you would expect.
The funny thing here is that everything other than this like little weaseling of randomness inside of the columns through this intermediate commitment is something that Celestia is doing anyway in their fraud proof based construction. So Celestia is taking this data, encoding it, which is exactly what we're doing. Just in the intermediate part, we're stopping for a little bit, catching our breath to generate a little bit of randomness and then continuing on with our encoding as before, virtually unchanged. So that was the real shocking part, which was like actually Celestia was running 99% of a Ligero prover already. Because Ligero is this protocol that takes random linear combinations and says, okay, if I take a randomly combination of these things and that's close to a code word, then the original set of things was close to the code word.
Yep.
I told them this. We're like, you realize that you're running a Ligero prover, and they said, what is a Ligero prover?
that was my question. Is like, was that intentional or had they rediscovered other insight? Yeah.
I don't think it's purely accidental. I think the fact that like they built this system with sort of two intentions in mind. One was you want to be able to process fraud proofs over just individual rows and columns, which is why you want this matrix. Because otherwise, if I could tell you if you only encoded in one dimension, you'd have to process a fraud proof, say, hey, this symbol is wrong. So here's like a whole bunch of openings, go decode this thing, but it's like now you're downloading the whole data to process the fraud proof. So they already had this sort of matrix-like construction that enabled the super efficient fraud proof. And it's a much simpler fraud proof system than, for instance, a general fraud proof system.
Yes.
That requires you, for instance, to run this bisection game to like figure out where the error was or whatever it is that these systems use. It was much more efficient in that you could just like literally very quickly check whether something was like exactly a code word or not, right, on the client side just by looking at it. So the fact that it worked really well for these fraud proof systems in order to have smaller fraud proofs and also make them easier to check than some general purpose computation turns out to also be the main reason why the stuff of checking the consistency. So you could either check an individual row or column and see that there's a mistake in it. Similarly, you could check individual rows and columns and check that they're consistent. Similar things seem to be happening here.
Exactly.
Philosophically, it felt like the principled reason why this thing works so well for fraud proofs turns out to be a very similar reason why it works very well for construction that's sort of validity proven. And it's that error correcting codes are magical.
Yes.
So I get my very quick question is like, so this the Ligero paper you mentioned, like, what was that for? Like, was it just a totally unrelated, like math focused paper, or was it something related to blockchain? Or
so the quick TLDR is Ligero is like is kind of an OG succinct proof system. It was very practical, very very fast, shockingly practical for like many applications, and in some ways, the inspiration for what became Fry and a bunch of other papers afterwards, but kind of forgotten because of that. Like Fry had these very small proofs. It was a very elegant system. But Ligero is like kind of it's beautifully simple. I mean, it's this idea, take a random linear combination, check that it's close, and that turned out to be good. But the reason it came up is because we had been studying it very, very closely because it's one of the few systems that is just like incredibly simple. Like the main idea is very simple. The proofs are very simple. We've come up with proofs for variations of it, along with Jim Posen and Ben Diamond, who also came up with other variations. It's just been like, in some sense, it's like one of those protocols that is, OG is very simple, yet like seems to have some sort of flavor of a bunch of things going right with it. And so it turns out to fit very nicely in a bunch of the frameworks that we have worked on, which is these old papers like succinct proofs and linear algebra and all this stuff. And from there, it's just like, okay, but a lot of things look very much like this, or could look very much like this system or this like idea. Why do we not use or expand that idea to like apply to these new?
Yeah. By the way, there was a predecessor to this in this paper called Foundations of Data Availability Sampling. And what I mentioned earlier, it was the same set of authors that then wrote this Frida paper that I mentioned Nico was looking into. The only thing we noticed was this idea of squirreling away these random linear combinations, the fact that you can use interaction to make the protocol more efficient. And sort of this randomness again of like, actually, could we make this truly zero overhead as opposed to a sort of low overhead? Was the second extension on top of that. So
to summarize, right, like you're basically doing two things, core things differently, right? Like the first thing is you have this, normally the way you're doing this encoding, you have like the skinny matrix you create. That's something you were doing before, but instead of just continuing and kind of doing the full transform on the other side, what you'll end up doing is actually pause there, apply like a small transformation, get this other thing. So like there's this middle step that's new. And then on the same time, you mentioned about basically sampling the intersection rather than so it also changes a little bit around how you actually do the sampling for verification. Is that correct? Or those are like
and that's the main trade-off right now, is that you're sampling these full rows and full columns, which again, you can make them very, very skinny because you have a lot of choice over field size or make the thing much more practical. But that's the main trade-off. You have to download full rows, full columns, check their intersection. And so for instance, in Celestia today, because you have like sort of this fraud-proof-based system, you can sample individual entries. KZG has this property. Well, KZG, if you do it only in the entries, just has a huge prover overhead. So you sample typically multiple entries together and do what's called multi-proofs to make the prover like at least moderately efficient, and reduce the overhead a little bit. But yeah, in practice, the main thing that we've looked at in terms of areas of improvement is kind of the resulting node size. So, but right now, as it stands, you can, and indeed Guillermo did this, like you could take the Celestia protocol as it is today, and with a variation of ZODA that has a little bit of overhead, literally prove today. I mean, nobody's out there in the network, and the nodes are configured to verify this proof.
Sure.
Not yet.
Guillermo did he had to do it in Julia just to make people angry.
Yes.
Including me.
We've ranted about this at length already. Like that whole linear algebra class we had to use. We had to use MATLAB, I think, for that. But there was this like aeronautics class I took where it was like deep learning in Julia. And let's just say that was the last time I touched Julia. But
that's why you're healthy and happy. Guillermo.
On the other hand, I'm not sleeping.
That's why I'm not walking into random rooms and scribbling on whiteboards. Yeah.
And then ranting at people like randomly on the hallway. So it's good. It's good for your health.
But Guillermo was able to do it. He just like something like 200 less than 200 milliseconds.
Yeah.
For like the biggest block that Celestia's had to date, I think it's been.
And so that the 200 milliseconds, so that's the proving side of it.
That's the proving.
Got it. And then the verification side is.
We don't talk about that part.
Got it. Yeah, not
the verification
work in progress.
He hasn't written the verifier yet, and so forth. Because and by the way, like you'd have to have nodes that actually want to verify these proofs and so forth.
Sure.
It's just like a totally orthogonal construction, which is really cool. Is that you can actually do a variation of this. You can't stop in the middle, of course. Right now, you can do this randomness a little bit later in the process. Turns out to be fine. It produces a bit of overhead. But that's the variation that we have. It's in Appendix E, I think, of the paper called.
Yeah. It produces near zero overhead in the sense that, like,
that's on page 50 or 60 of the paper.
Yeah. I don't know. Actually, it's even that long.
We don't do that kind of stuff. Right?
Yeah. We don't write the normal.
Yeah, I know, Patrick. You read a lot of consensus papers. This is different.
That's the last 30 are just ChatGPT or what?
Yeah. The whole thing. Tap. No, so I mean the answer is this particular variation is cool because it's actually literally zero change in the sense that you can create proofs for Celestia today, And the proofs are not zero overhead. They're not literally like don't cost you anything, but they are near zero overhead. And it says that like as the block gets large, you know, the actual proof that you have to send, you send a separate proof from the block itself that verifiers can then use to like check the rows and columns are good. Becomes like, you know, like becomes 0% of the entire communication for samplers as the block size gets larger and larger. So right now, I think the overhead for this proof was something like I don't know, like 10% or something. So so in other words, like samplers would be sampling, and like roughly a little under 10% of their total communication, or 5% of their total communication will be the proof. Will be this like proof that doesn't help
this
you.
Portion of the proof.
The rest is just like actual rows.
The data. Yeah. And so then the trade-off is that. So I guess like you just get one row and one column, or do you have to pull multiple? I guess.
Yeah. So as a verifier, it depends on how much you know the
confidence
more
you want. I guess. Yeah.
Exactly. The more rows and columns you want, you know, you get the more confident you are that the thing was actually good.
Good.
So there's a whole discussion to be had.
Both correctly encoded and available with the same samples. That's the idea.
Yeah, the goal obviously is to try and hit some sweet spot there where like you're both accomplishing the availability component and the correctness component that you're trying to.
So they're both the same.
Obviously.
What's cool about this particular thing is that they are identical here, and this was like any samples that you do for validity, you're also doing for availability. Like they're the same. Right. The work is just completely reused. The only thing that would not be reused, quote unquote, in this like new scheme that's not ZODA is you end up having these like extra little tidbits of proof that you now need to use to confirm that indeed like the things are consistent.
Got it.
But you get zero change from the existing construction.
Yes.
Which is what, you know, you buy for that a little bit.
Okay, got it. So like just to confirm that, so like during in the ZODA construction, you like kind of have this intermediate part where you do this randomness stage, and you're basically saying that we don't need to do it exactly that way. We can kind of get the same property and then just basically addend it or like add it to the existing coding process, and it like kind of does the same thing. Yeah,
exactly. Like additional metadata from like you could
got it.
Celestia block that themselves are like help you prove that like if you sample rows and columns, you're good.
Yeah, we can talk a little bit about accidental computer stuff, but like one more small note here is one of the cool features of ZODA. Actually, it's a good feature of the 2D KZG construction that Ethereum has as well. Is that if some portion of the data is missing or otherwise corrupted, that once again, just as you can process individual row, column fraud proofs in the current Celestia construction, you can also reconstruct missing components without needing to process the whole data, which something like Frida doesn't give us, and a lot of other constructions don't give us. So people, and both of those constructions, the 2D KZG one and ZODA, have like square root products in terms of verifier complexity to download and also to work, also verifier work.
And I'm guessing that like you mentioned that like maybe you can reduce the burden on the sampler by like making the rows or like basically increasing reducing them the size of them a bit. And I'm assuming that puts more weight on the prover then, or like it takes more time to prove because you have more columns or rows to like end up doing if the individual pieces are thin.
There's a soundness limitation on it, so at some point there comes a trade-off, and also you can't make them too small because you need there to exist like reasonable Reed-Solomon codes over the thing. Guillermo, you can jump in and correct me here, but if the prover's just chilling, the prover's fine with all of this.
Yeah,
the thing like for some reasonable ones, you do want smaller fields because there exists like really efficient ways of encoding, like 2 to the 8, 2 to the 6.
Yeah, for context, right? Like the point is like the prover here is only doing encoding, and encoding is like hilariously fast on a lot. I mean, it's like you can do 128 megabytes, 256 megabytes, like a gig in like a few seconds on a laptop type of thing. Like just like that's the number we're talking about, and like again, that roughly is like itself a proof, right? There's additional overhead from a little bit of other stuff, but like the point is that's most of the work, and that most of the work is already done and very quick in practice today, like on a laptop. Right. So
the dumbest example or basically explanation of this is like you're already doing all this encoding work to get this like Reed-Solomon,
and it's already fast.
Some variant of it. I mean, it's super optimized. It's used everywhere, right? And then you slightly tweak it, and all of a sudden, like when you actually sample those pieces, it's verifiable, and you know that it was done correctly somehow. Which doesn't seem possible. And now, on top of that, you're telling me that it's also a computer.
Yes, correct.
How?
This is the magic. So I'll preface this, and I'm going to let Alex give the good TLDR on this, but I'll preface this with like this is my like, annoying conspiracy theory shit of like true decentralization has like never been fucking tried. And like, this is our attempt at it. This is like your phone should be able to verify like the entire blockchain, including availability and all of the stuff without downloading the entire damn thing. And like your wallet should be constantly verifying the blockchain and making sure that like your stuff is good. Like you shouldn't need to depend on like a bunch of RPC endpoints at like, some random AWS server somewhere in the middle of nowhere to like ensure, and you need to trust them to ensure that like your balance is good. It's like, come on, dude, like what are we doing here? Like
you don't trust AWS?
What's up?
You don't trust AWS?
No. I do not trust anybody, not with my
we should do this stuff with the same philosophy of we should have insane performance for actual users of the chain. Like, sure. I think we've seen these things as roughly in opposition to each other. But it turns out that a lot of these techniques are not real. There aren't really trade-offs to performance. If anything, they are enhancing of performance.
Mm-hmm.
Like, so if you think about it, actually, like for performance reasons, like Solana also encodes their blocks, right? You want to compute Reed-Solomon encodings in order to ensure that you propagate things more efficiently in networks, and because mistakes can happen and people can be malicious. Like this stuff is not just because we have some like crazy, come and take it type of like decentralization minds and want to sort of nerf all the systems to make them slow. Actually, this stuff oftentimes is in service of greater performance and also in some blocks verifiability. That's not always the case. There are of course trade-offs, but in some of these dimensions, that's actually not true at all. So anyway, where do we come to the accidental computer? Okay, so remember we said, okay, one original idea. So like consider the sort of construction of a rollup. A rollup has some data, some transaction data that it wants to process. So it'll take that data, it'll post it to Ethereum, it'll post it to Celestia, whatever. That data will then be encoded and hashed as part of this nice matrix we've been talking about so far. Okay, then the rollup is going to prove some statements over that data. So taking this data that was posted to the data availability system, running it through the state transition function, outputs this new state. So mechanically, what's now happening? So number one, we're taking that data, we're encoding it, we're hashing it. Before we were talking about even taking that and putting that inside of RISC-0, which would have done a whole bunch of random reductions and then would have taken the data, encoded it, and hashed it. And then we're going to take our state transition function and stick that into RISC-0. It's going to take some data at the end of the day, encode it, and hash it. And then people are going to sample all of the above. And that's going to be like our nice proof that the data is both available and indeed that the state transition function executed on that data is correct. Great. Well, that's 3 redundant encodings and hashings, which are the concrete bottleneck for all 3 protocols. So what if ZODA is like, let's take 2 of those and sort of not do that? And the accidental computer is like, what if we actually just do this once? Right? What if we notice that this encoding and hashing, just as we notice that, again, these general purpose compute primitives that like, ZKVMs and so forth are at the end of the day, reducing things to encoding and hashing, but that turns out to be like a fairly general thing. Like it tells us something much more interesting than just that the data was correctly encoded. So yes, something like Celestia was running a Ligero prover that was proving the correctness of its own encoding. But it actually also, it was proving something much more general at the same time. So not only did we not notice that we were proving our own correctness, we were actually also running proofs for much more general stuff. We just weren't utilizing that work. So it turns out that there exists, like the simplest way to sort of construct this into what's quote unquote a computer, actually not quote unquote, like literal computer that's verifiable, is there exist these protocols that only commit to the input. And maybe more general constructions of this type of thing exist, but for this note that we just put out, we use these protocols because it's super simple to see. So if it's matrix multiplication, the Stanford linear algebraists will know that matrix multiplication is a very common operation in basically everything. They're just really efficient interactive protocols for matrix multiplication that really reduce the whole operation to just checking something about the inputs. In other words, the matrices themselves, which you can commit to ahead of time. And really, you don't need to read the whole matrix. You just need to know the evaluation of the polynomial that matrix corresponds to. For example, there are just other protocols that are called this GKR protocol is one more general such construction, which takes the inputs to a computation. So I send you the input, we run a whole bunch of interaction, and then at the very end of the day, you're going to check the evaluation of the polynomial corresponding to the inputs at a point. So that was what we looked at. And it turns out that given the fact that you already are encoding and hashing the input, that turns out to be a polynomial commitment to the data, to the input data. And so now I can find a general purpose computation over that committed data. Now I'll send you the output to that computation. We'll run what's called a sum check protocol on a bunch of layers that iteratively reduce this to a claim about the input data. And then you're just going to open that commitment at a point. But what's opening the commitment at a point? Getting the evaluation of that polynomial. What do we call that? We call that data availability sampling.
Yep.
So what are we doing in data availability sampling? We're like getting evaluations of the polynomial at a bunch of points. And if you get a bunch of them, again, the linear algebraists can correct me, but you can invert the matrix and get the original polynomial, and that's what we call data availability.
Yep.
There is matrix inversion, yes.
Yes, exactly.
It's that, I presume.
Yeah, something like that. I mean, my gut reaction to it is always just like, no way, right? Like, like it's kind of crazy that it all comes down to it. I mean, like, I guess like the core, like fundamental thing here is just like polynomial commitments are extremely powerful for like representing arbitrary computation. Well, not maybe fully arbitrary, but like I was reading, like reviewing for this, and I saw this like line, which is like any finite computation, you know, can be represented as a sequence of additions and multiplications over a finite field. Which, if you're wondering like how I take my code up in the sky and turn it into these lines, like that's what's going on here, is that you can actually transform it. Yep. And so if once you have it transformed, this is where all of this stuff becomes extremely useful.
Yep.
Yeah.
Exactly. Yeah. I mean, it is like, you know, we say these steps very casually, but it is like a little bit of like, you know, magic that like all of these steps all like boil down to kind of just some evaluations about a thing. And it turns out like, again, by sheer magic, like that's already what we are doing when we do data availability sampling, because like by definition, like roughly speaking, the thing you like, it's kind of wild. Like, you know, the whole observation is, again, very stupid. It's like, what are we doing? Like Alex said, we're encoding and then we're hashing. And then we like take that encoding and hashing, and then we put it into another thing, which then encodes it and then hashes it. And then we put it into another thing that encodes it and hashes it. It's like, why are we doing all this work? Like there's no reason to be doing all this stuff again, over and over and over again. So can you like just like collapse the steps in the middle, right? And so anyways, the final point here is like, we called it the accidental computer, because Celestia, for like its entire existence, has been trying really, really, really hard to like try its best to like not enable general computation to exist on its layer, because that like brings a bunch of complexity. It brings a bunch of like extra things that you need to like now take care of in terms of security, in terms of guarantees, in terms of what you want to do, like what node requirements are. And yet they still built a computer, right? Just by doing this like very basic encoding stuff.
So it'd be a shame. There's a really nice encoding hashing scheme you have there. It'd be a shame if somebody ran some sum checks over it to make it a computer.
Yep, exactly. So that's the final observation.
So wild that that's the end result of it all. Because I guess like, I mean, especially now with like this increasing focus on like ZK verification, well, you know, ZK, whatever named, Stark and Stark, you know, computation compression, and like the idea that you wanted to, you know, they're interested obviously in having like accounts that utilize this, and the idea that all of a sudden it just kind of, it already works is a pretty crazy accident.
That's right.
Yeah, man.
Yeah, like in some
I wish
sense,
I was that lucky. Jesus. Yeah.
Well, we do have one for you actually. So here's another way of looking at this, which is like sort of leave data availability systems to the side and think about sort of an integrated blockchain design. Right? And you have some computation that you define as your state transition function, as you must, right? And you want several of these independent systems to be able to talk to each other in a trust minimized way.
Sure.
Right? So one way to do it, of course, is like I can trust the validator set and I can run like a light client of the other. Right? But if I don't want to do that and I want to have full verification, I need to verify that the state transition was executed correctly, and I want to ensure that the data is actually there so that those validators withhold it from me, and I can still reconstruct stuff and like get my money out, for example. Some conditions. Well, cool. It turns out the most zero overhead construction is one in which the proposer of the block is aware of both the data and the computation. So in the example of the rollup, the Celestia node doesn't, like the Celestia proposer doesn't know anything about what you want to, they just arbitrary blobs. Like they don't know, they don't care, they shouldn't know, they shouldn't care. And so now you need to go define a bunch of stuff over it to get like the full computer. So it turns out to be like fairly super efficient and fairly low overhead to do it for a lot of very reasonable protocols. It's just a bunch of sum checks, and the hard part of the encoding stuff is handled by Celestia. But in the system, actually, where you control all of that, it can be truly made to be zero overhead. In other words, you get the polynomial commitment scheme that you run is exactly the same one that has awareness of the computation. And as such, there's zero additional polynomial commitment scheme work that needs to be done. So you truly get what are called sort of PCS-free zero knowledge proofs. And it turns out that a lot of zero knowledge proofs, the PCS part is like the concrete bottleneck.
Yeah.
And so you remove all of that, make it a lot more efficient to prove both validity and availability in the same system. And now you have these full sort of layer one, fully sovereign chains that can talk to each other and pass around availability proofs and validity proofs of each other that are very, very low overhead to compute. And already, even in the construction that we have today, which is based on this GKR stuff, you could imagine very reasonable practical versions of this. Like one example is, I know you and I chatted a little bit about some of these CRDT-based systems, like Farcaster snap chain stuff and so forth, where really you're already in this CRDT sort of commutative world where I just validate a transaction, maybe increment a counter that's like a like, right? And I only do that per account, and I think they do some kind of fancy sharding in their case, kind of more in the night style. Like that sort of system, now I don't know the details of it super well, but like that sort of system is highly amenable to super efficient, like data parallel proving that like GKR and these systems are really great for. So you could imagine like a really efficient, like heterogeneous or like homogeneous sharding system that again works in this sort of integrated manner that becomes super efficient in this way. It's not just the, roll exposed thing to a data availability layer.
Yeah, I mean, I think the problem has always been, right, that like there was that phase, that fever dream we went through where we're like sharding is going to be sick, and then we like people all committed to sharding, and then like hard pivot out of sharding because it turns out like the committee and like the recovery stuff of failed committees kind of sucks. But as soon as like all the computation is just provably valid upon discovery, like the theory, at least what I've been operating under, is like all of this stuff is going to remake a lot of the architectures of existing chains, because like you can seemingly do stuff that forever we've been designing around to like not have this problem, but all of a sudden it's like, oh, it's just getting the data itself is actually just it. Like that it's valid, that the transfers went through. Like doesn't seem possible, right?
So this is the thing. Like this is like, and this is I don't know, which is a crazy set of ideas, but like it's like we've gone for like the evolution of blockchains seems to go like we start with a thing, and the thing only enables like transfers and like a little bit of code, and people are trying to make it enable other stuff, but like fundamentally it's quite difficult, namely Bitcoin. Then people put like, they're like, sick, this thing can like support a machine, right? Like why do our situation functions only have to be like transfers and it's like some additional Q opcodes? So it's like now we have a general purpose computer, but it's like, oh crap, but like now to verify the entire chain, you have to like start from the beginning, run the entire thing all the way through until you get to like the front of the chain. So people like then split off into two little camps, right? Which is like, cool. Number one is let's like put the data such that like you don't have to like download the entire chain to like know that things are available and like all the stuff. Let's put it into like a like layer that allows you to certify that, but still deal with this mechanics of how do people, make sure the current state is good. That's a different problem. And there's like the other side which is cool. Like there's this thing called succinct proofs, which allow us to prove that things are good and correct and like we're chilling. Except now you have this problem with the data where it's like, okay, yeah, but like, what about like, how do I get my bank account balance out of this thing, right? So, the point is like, okay, like we did the split, and then there's kind of like weird merges in between, and it's like now like wait, but like what if we just combine the two, right? Such that like the actual overhead of both verifying the data and verifying the chain itself is very, very small, right? Like it's actually literally like as small as running a light node on this chain. And that light node has very strong guarantees about everything that has happened on the chain, right? And that, like you said, is exactly it, right? Like you now can like run chains as if they were like multiple separate chains, right? And then they just prove stuff to each other. And like, that's cool. Like that's totally fine. There's no problem with that. right, separately, right, you could prove things about chains, and then somebody else can just come very quickly verify without needing to depend on some external dependency of like, okay, some oracle is telling you that like actually, today your bank account balance is whatever, right? So it's like, this is like truly the like, this is like decentralization TM as like God intended, maybe. I mean, hopefully, right? But like, this is the thing, like in some sense, like it's weird that we've kind of gone and reinvented the whole wheel to like run ourselves over. But now it's like, okay, cool. Like,
hey, but we're here, like. The great thing too is it's like plausibly post quantum, right?
Yes.
So then now the next part that kind of gets crazy with it is because like typically when you're doing consensus, you will accompany like a proof like this with maybe some proof of consensus as well. But like if you include that in the construction of like the state transition function itself, like not every consensus protocol would let you do this, but like you could do something like this. And then if you used, so there's like this whole string of, like post-quantum cryptography going on for like asymmetric, whatever. But the problem is they're huge. The signatures are massive. And so if you just get away from the problem entirely and actually just say, you don't actually have to download all those signatures or like all this massive stuff. You just have this massive matrix that you can sample and like, that they're both like correct signature encoding. And then you can do crazy shit like recursive multi-signatures. Like you can do like all this post-quantum shit, but it all boils down to commitments. It's crazy.
Yep.
Like
I haven't looked at these in detail, but they do have, for better or worse, this is more spitballing, but they do have like a lot of the hash-based aggregatable stuff that people have been looking at. Like this sort of stuff does have the flavor of like, it's again the same tool as like we're doing hashes, we're doing encodings, we're doing stuff.
Exactly.
So
there's like the two
like proving those things like has a similar kind of like weaselly trick like Guillermo's been able to come up with some of these other ones. And like the idea could be
those weaselly tricks, Guillermo.
This is the worst part. He blames it on me, but it's him.
This idea of actually, if you're trying to prove or verify sort of consensus, oftentimes like it is actually highly amenable to this type of proving too. Like actually, there's a reason why. Like if you look at like the ZK bridge constructions, they're built with sort of GKR like approach. Oftentimes, is because they do have. You can sort of again be able to create a lot of data parallelism out of it. So again, like you could think about it as like decentralization is like sort of this hard constraint, but in practice, like it's also the same thing. Was like when we looked at these sharding based systems originally back in the day, it was for performance. We weren't looking at it out of just pure decentralization maximalism. And
right,
like well,
the opposite maybe
hard and like it was exactly it was the opposite. But a lot of these problems have been super hard, and it's like, well, should we just like try to figure out how to do it all in one place? And that's been sort of this big debate, as Guillermo shared. But like, look, if fundamentally you can have these chains like interoperate with each other with essentially zero overhead, these sort of parallel constructions, and that the user barely notices it because the proving and the verifying is essentially zero. Now, I don't need to download, like it's great that I don't need to download all the data. It's not just because my node is really tiny. Even my node's really big. Great that like nobody on the network needs to download the whole data if they don't need to compute stuff over that data. I can just download the data that I need to compute the part that I need and prove to you that I did it well with ideally zero overhead. And now you don't need to do that work.
Yep.
So that's not just like a more decentralized system. That is a more performance system.
Yeah. Yep. The idea that, I think the core thing there is like the idea that the throughput or like the bandwidth usage can exceed that of any particular node being able to, which is crazy.
Yes.
And I think like the other trend too for like, people I expect listening to this are already familiar with this relationship, but like the inverse relationship typically between throughput and then verifiability for clients is also just goes away entirely. The context for how we've thought about it prior to like these sort of like God tier, whatever ideas is like that we, you use threshold signatures as a means to like have a succinct representation of like the consensus set and design it. And then you basically assume that as long as like the set hasn't been corrupted, that like any threshold signature must be over valid data because like they wouldn't have otherwise
Right.
produced a consensus signature over it. But it provides no guarantees or like natively around availability, or that you yourself can actually verify the output of that computation's correctness. You just basically take the word for the validators, because if that's broken, everything's broken. So it kind of takes this reductionist view of things. But like, yeah, that's not post-quantum. It's also hairy because of the resharing procedures involved with all of the threshold stuff, which are extremely complicated to do in like an asynchronous environment. And so the idea that instead you can have some version of this that like also, it also doesn't solve the problem of like having like this kind of integrated sharded construction. So, you know, baby steps, right? Like we got to make it work before it can do really well. Yeah.
And like, you know, we're out here pontificating and you're out there actually
building stuff. Yeah,
but,
exactly.
you know, an ideal world, like, yes, I think eventually there's going to be some trade-off between this like verifiability and performance. But I just think it's ridiculous to claim that we have like found the efficient frontier already, because all these things of zero overhead or very close to zero overhead, proving constructions, data availability constructions, and the like have indeed, at least to our eye, shifted the curve out.
It's crazy to reframe it as the same problem. Yeah, I think like that's where it's usually lost, is like people's, you know, like it's almost like you have these people that are like performance, low fees at all costs, and then you have like the decentralization people come in and they're like, whoa, we can't do it that crazy. So the idea that you could somehow align them seems
literally,
to
¿por qué no los dos? Like, are you serious?
Crazy.
Like, why are we just like even debating
this? I don't think our systems are like, we've figured out the conceptual limitations of our systems enough in candor to say, again, we are on that, like different people, like there will at some point be like an efficient frontier that trades off these things. But I genuinely don't think that we understand that frontier yet, because we're not there.
Yeah, that's crazy. I mean, I think like a lot of the ideas are, I mean, like if you believe that like succinct computation verification is like going to happen, and then you also believe that like we need to support like a significant amount of throughput on everything, like that no machine can handle all that throughput, you know, you arrive at this problem like, well, now what? So so I mean, I think that's a great transition point to, you know, where is the research at today? Like, are you about to drop another thing tomorrow of like another further extension of all this, or is it you know, you're teams to implement it, or that
would be crazy, both the implementation and the dropping it. That would be, who would ever do that? Like, why would anybody ever do such a thing? So the answer is for implementation, currently working on a verifier, which turns out will double as a interesting prover for something in the future. There's something very magical about this whole thing.
These researchers always have 5 games going on at once.
I know.
You got to be careful when you talk to them. Yeah.
And then, so that's part one. So that's kind of the biggest one. And then I don't know what else. I guess there's some maybe potential future work around like, you know, some of these sharding and like, you know,
trying to make it work.
Well, like network, you know, assumptions on these kinds of models. Maybe that's too much alpha, Alex, but you know, we've been thinking about
node size stuff on ZODA, which is related to what Guillermo just said. Thinking about cleaning up some more of the basic notions of data availability, I think would be a very useful thing to do in general. And I think there's also good generalizations, by the way, of the most recent paper. We just gave like one construction with like one particular PCS and one particular what's called IOP, Interactive Oracle Proof. There probably exist more general ways of looking at this whole thing, that these types of connections are sort of wider, occur in more areas than the ones we just looked at.
So that's how it will happen. And then hopefully at some point making it, you know, not just like verifiable in the data sets, but also like having people start using the accidental computer part.
Plugging it all up seems kind of crazy. I mean, I know we've gone for some time here, so I do want to wrap this up here shortly. But the other thing that's, I guess, like you mentioned, that there's particular types of things that kind of work well for these like PCS free constructions. Like, are we talking things like simple transfers, or are we talking things that are even, you know, like pushing the boundary of like what that might even look like? I don't know if there's any particular paths you've started to explore on like how to actually instantiate it. But
I think Alex is the more knowledgeable.
Yeah, so this is part of the generalization, which is right now we have one specific construction. That specific construction happens to work very well for operations that are data parallel. So if it's something like payments, you could imagine that being done in a highly data parallel way. Of course, there's ways to do it that are not that, but in a general sense, you could. Things like verifying consensus. Verifying these sort of more minimal constructions. The Celestia app today, for instance, is not a full virtual machine. It's not a turnkey.
Sure.
You just verify some balances, some signatures, very similar to the consensus verification. Those types of things are highly amenable. The stuff that I mentioned earlier, CRDT style systems, like the social media interactions where you have per account updates that you want to prove and verify, that sort of thing is really good. So there's a series of these that, machine learning operations.
Yeah.
Right. Like
Right.
These are,
gotta drop the AI and makes sense. Yeah.
Yes, these are, typically you'll end up with these very wide and shallow circuits. Those are great for this type of thing. And oftentimes we will end up with a lot of data parallelism. In fact, the Modulus team that was acquired into World has been a team we collaborated with on this paper because they've been really blazing the trail on very efficient proving for this exact type of computation. So if you want verifiable inference operations, for example, these are the types of protocols you would be using anyway, it seems. And so it's very easy to imagine that those could plug in very naturally.
Yep.
Those are the things we know right now, and I suspect there are generalizations of these. But already, I think those are quite practical. You could do very.
Like the thing is, right? It's not like you can't like use it for more. It's just like this is
right.
the optimally efficient, like zero overhead kind of computation view.
It's also the things we've just looked at because it's like the thing that this particular, proving system is suited for. But like certainly, I'm sure if there's kind of like this thing is very good at this, but we also have these other proving systems, right, that are like good. The problem is like there hasn't really been a reason to maybe explore this particular proving system more broadly than like the things it is very good at. Whereas like this might provide a reason to do it, right? Like maybe it's actually possible to construct like certain common operations that we do fairly quickly in this proving system in a way that's actually quite efficient, but just nobody has really thought about it because why? You already have these other like much more efficient proving systems for those types of things, and like it intuitively feels like maybe that doesn't fit super well with this. So
you're talking about a refactor of an existing system. That sounds like something we don't need.
Yeah, we don't. Usually a hard sell.
Exactly.
That's funny. Yeah, I mean, it'll be. I think the same thing happened a time like where blockchain kind of just stumbles upon these things that people created a long time ago, and they're like, actually, it'd be great if we if we had these really fast and really well proven, and then all of a sudden it's like we figured out how to prove all these impossibility results that we would have never even thought twice about 20 years ago or something like that. And by we, I mean not me, but someone else. And but it's great to use it. So. Yeah, I mean, I think it's crazy what you guys have done in this December.
Far too kind.
So I mean, the last 6 months or so, pretty good. So I mean, it'll be really cool to follow along and see where this goes from here. And it sounds like you guys are already talking to some teams about incorporating it and using it. And I guess are there any parting thoughts you'd like to leave us with here? Both on like being, like some of the research you guys are doing, if you're trying to like collaborate with anyone in particular, or anything that would maybe where people can find you if they're interested in learning how they could use something like this.
Yeah, you can find us. We're on Twitter. We're on Blue Sky. We're on basically most of the messaging applications, for better or worse, being as we are in the sector. And so we're pretty easy to find. If you want to collaborate on any of these things, or this sparks questions or potential inspirations for new directions, there's a lot of work still to do here. If this is of interest to you for a particular construction or protocol, would love to hear from you. We really enjoyed this conversation, Patrick.
Thank you, Patrick.
The advertising for this, we could go on reasonably deep in various technical directions, which is a very dangerous statement to make.
Indeed.
Hopefully didn't make you regret that one too much. But
no, I feel like I did what I could, and you guys kind of took me. It's fun to ask questions and not be responsible for the answers. So thank you for the thoughtful responses to everything. And I'm really excited to do the necessary follow up here as we learn how this is used, and like maybe the next wave of insights people get from actually deploying this in practice, which could be pretty cool. I'm not going to ask anyone to learn Julia. I'll stop there. But if is your code public on like how this works, Guillermo, or
it will be soon. I want to
Cool.
finish the verifier. Currently working with Andrea, another team member, on this kind of stuff. But hopefully, once that's done, we'll actually have even a nice Julia library to do finite field stuff. We'll have like codes to do verification and proving, and it's very fast and all this stuff, blah blah blah, all the nice fancy things. So, but hopefully,
stuff I can feed into ChatGPT into Rust. So
ideally,
it's all good. It's all good.
It was meant to be.
Happy. That's the idea.
The Rosetta Stone of our era. Yeah. So the I think it's it's been great to have you guys here. Appreciate the conversation.
Thank you for having us.
Thanks for the first episode of how things work. Hopefully a sign of good things to come. So all right. Thanks everybody.
Thank you again,
Talk
sir.
to you later.
Take care, Patrick.
Ciao, ciao.